Okay, welcome again to International Sound Conference 2015. I would like to introduce the Cosmo project, right? Alex Hoffman and Bernd Isaac Verstedt. So, please, welcome to our guests.
Let's use this one. Yeah, hello. My name is Alex Hoffmann. I'm from the Music University Vienna, and I'd like to talk with Bernd Isaac Verstedt together about the Cosmo project. You've seen it here in our very short demonstration. What we do is that we have standalone boxes where C-Sound is running to do live processing of incoming sounds, like from the guitar, from a microphone or whatever. And we want to guide you a little bit through this project. What is the main idea about it? The main idea is to have C-Sound on a do-it-yourself project so that you can build these boxes. And the whole project started in 2013 on the Linux audio conference. We met Edgar Berdal, and he was giving a workshop about the Raspberry Pi and about running PD on the Raspberry Pi, and doing his project was called the Satellite, Karma Satellite, to have standalone devices for installations or whatever. And we both met and thought, like, that would be perfect to integrate C-Sound into a live performance setup like you see here, with multiple other effects, having these quarter-inch connections, but you want your unique own effect, and you want to put C-Sound in the middle, and this is what we want to do. So this is what I said. Yeah, we want a seamless integration of our custom-designed effects into our existing live electronic setups. We don't want this complicated setups on stage, like having a computer, having a sound card, having controllers and everything. We want everything in one box so that you can easily set it up and you know that it's running. And the nicest thing is, how you see here with this box, or the other one which is over there, you can make a custom interface design like you need it. Like the distance between the knobs can be, like, if you want to control with your feet, you make a different distance than if you want to just play it by hand or whatever. So how we're going to approach that is going to be explained in the next slide. Yeah, the Raspberry Pi, most of you probably heard about it as well, is a microcomputer. It's just that size of a check card. Now we have the second version that came out last year, and it's very powerful. It has a quad-core ARM CPU and 1 GB of RAM. And the most interesting thing for us, also in comparison to the satellite project from Edgar I was talking about earlier, is that we do not use Arduinos to interact with the Raspberry Pi. We use the 40-pin GPIO header, which allows us to connect all the controls to the Raspberry Pi. I think Bernd will go on from here.
Yeah, so the initial design we had 2 years ago was quite simplified, and then we got an electrical engineer named Christopher Koch on board, and which helped us to make this a bit more fluently. So he designed the Cosmo hat, and the hat stands for hardware attached on top. And the features of the Cosmo hat is 8 analog inputs, controller inputs. It's got 8 digital inputs and outputs. And you can select which ones are ins and which ones are outs. It got MIDI in and out, and it also got some output for digital LED controls, some LEDs called VS2812. So that's an untested feature yet, but these LEDs are digital LEDs with integrated circuits on each LED, so they can be controlled like individual pixels or screens or whatever. So a run through of the Cosmo hat. We have the top here. We have the connection to the Raspberry Pi through the 40-pin GPIO header. And here are the 8 discrete controller inputs outputs for switches and LEDs. And down here we have the 8 analog controller inputs. Could be used for pots like this, but it's also possible to connect it up to jack input for expression pedals or any type of continuous sensor you want to build in. Yeah, and it's all controlled by a microcontroller with easy access through a custom Python library that we made. So it's sort of a bit the same as an Arduino, except that it doesn't require any programming. There's a pre-run script, so everything is ready. And it's all connecting directly at the GPIO, and it's also got already MIDI in and MIDI out, and I think also more analogs in than at least the normal sized Arduino. So yeah. To build this, we have to connect all the pots like this. Adds up to a nice cable chaos in here. And everything in the end is then connected to the, here you can see the Cosmo hat sitting on top of the Raspberry Pi. So it's quite, and these are the digital connections on the right-hand side, and in front you got an analog in. So it's actually quite compact also, which soon enough turns into a problem when you add knobs and switches and a lot of cables and stuff. It might look like a big box, but it fills up quite surprisingly quickly. As for the audio handling, we have thought of this circuit. Depending, it might. This also might change depending on the wishes or the feedback from the users, but this is what we have now. So the input goes both to straight to a through bypass toggle switch and also into the audio interface, which for now we're using the Behringer UCA 202 or 222, which are very affordable, small, and runs on Linux. And the sound quality is more than okay. And the output and the input and the output from the sound card get together in this wet dry, analog dry wet mixer. So you don't have to run your, be afraid that you lose signal quality on your dry signal running through here. So you can just use 100% wet effects in CSAM, for instance. So in the box it looks like this, not as a bit more chaotic. You got audio in going through the 3PDT through bypass switch and the audio out, and this is also connected to a LED, so you can see it lights green when it's on and red when it's just going through. for this build, we haven't managed to finish the dry wet circuit yet, so that's gonna fill up a bit more. But we have the schematics and we tested the circuit. It's just not built for this yet. Also important when building this is the ability to control this without opening the box up all the time. So that's why we added the Ethernet and USB control or connections on side the box, and we made a simple big round hole and 3D printed socket to connect it all, so it nicely fits together. So as you can see here, I'm going to show you the workflow a bit later, but it's only connected now through a normal Ethernet cable to the box, and that's how we can control it. For power, we wanted to use 9 volts because that's the standard for the guitar pedal design. So we have this step-down transformer. At first we made one ourselves, but you found out there was a very functional one, very cheap ones, like for Deal Extreme. So, and 9 volts is also more suitable for the audio circuitry. So it's a step-down transformers to give 5 volts power input to the Raspberry Pi. And when it all comes together, it might look something like this. So it's a tight fit. So the way we use CSound is that we run CSound through from Python through the CSound API, and then we have our custom-made Cosmo AVR open source library to get the controller inputs into Python, and then we're sending it on to via CHN channels to sending and receiving controller data. This might be also very easy for someone who for some weird reason wants to use something else than CSound. It could just change from CHN channels to maybe send out OC messages or something like that. So quick workflow demo. Just have to get up the... So the way it is, it's a bit unseeable. Try to make it bigger. So we just use SSH to log in to the Raspberry. Takes a bit of time. And then there's also very handy to just use the like an FTP client like CyberDuck to actually, when you want to go in and edit the CSD files, and if you save it, it will update. So there's a main Python file now. Actually, it's here. So you just choose which CSound file you want to run, and then, well, all this code down here, it's really not necessary for anyone to change if they don't want to. We want to. It's a point to try to make this as easy and accessible as possible to most people, so they don't have to, so they might be able to use this box without any serious knowledge of Python or anything, and just like a very basic understanding of CSound, I think.
Let me add one detail. So on my box, I already made a patch that I read the CSD file just from a USB stick. So I can edit it on the computer, and whatever I put in here, then it boots from this USB stick and uses it. So that can also be a way so you don't need any SSH connection to the Raspberry Pi.
Yeah, so that's one of the, it could be several. This is more for a workflow for development, not for when you're running that. So of course a better solution. But if you want to try out the things and work on your projects directly on the Cosmo, you can just go into the CSD files. Let's open, like, for instance, the reverb here. So it's very simple code, really. Just putting the CHN gets in the include file and do some scaling and running the input sound through the reverb SE. So anytime you want to, change this, maybe you want to change the scale or something, you can just go in and do the changes here and then run the Python script again. Oops. Wrong folder. And then you will see that we put in, so you can actually see the values. Now it's going from 0.4 to, yeah, cut off here. Yeah, I think that's it for the workflow. That's in the Python script, the one you run. So you just choose it in the top here. Now it's running the reverb thing. You can try play a note on the guitar. This one. All right. So I think the workflow now is pretty neat in a way that it's easy to go back and forth and continue. So the sound demo we just did, and okay. So about the workshops. We want to do this as a series of workshops, and as mentioned, as easily accessible for most musicians as possible. That's why we want to have ready-made patches and everything. So it's even though if you don't know how to design your own CSAM patches, you can just use ready-made or from others. So what you do is you sit down and you enjoy some soldering. Then you make your own design, which Alex mentioned. So just choose the knobs you want, put it out, then you drill the holes, and in the end you will get your finished design. So this is the 3 different designs from a test workshop we did in Oslo in end of August. Yeah, and I think that was one of the most fun thing actually for the contestant to be able to make their own design. And of course now we chosen the guitar pedal layout for this, and this is just to keep it a bit consistent and get through it. But of course you can add this into any type of shape and size of a box. You're just limited about the amount of knobs and stuff like that. So we got funding from the Norwegian Art Council, and we, as I said, we had 1 test workshop, and we have planned for 4 2-day workshop in Oslo, Bergen, Trondheim, and Berlin. And there's also an integrated part of a public Cosmo performance of the workshop, like we're gonna do on this conference tomorrow. So it's sort of like an artistic demonstration. And I feel it's important to not only do the technical side, but show the artistic way.
So what I want to say at this point is that we have these 4 workshops planned, but if you are in some institution in some city and you like us to come there and do a workshop, yeah, we're very happy to visit your institution and give these workshops.
Yeah, and then and a very natural question in the end here is probably what's the cost of this? So we put together an approximate cost of components, and this of course might change due to currency and availability and stuff, but the total component cost will be 170 euro or 190 US or 12,500 rubles. And covering other expenses, the total workshop cost will be equivalent of 245 euros or 275 per person. And then you will get 2 days of workshop with us, and you will go home with your brand new Cosmo box in your pocket. So that's what you would pay for a not too complicated normal guitar pedal, I think so. I'm not sure. I have to think about it. We can discuss a business deal. Yeah. So the future work, to sum it up here now, is that we are going to build a website for this. For now, we just have the Facebook page, but we want to have a forum. We want to put out the build instruction, the PCB design. Everything is going to be open source, open hardware design. And also, importantly, an instrument/effect library, probably served on GitHub or something. We need to fine-tune the audio circuit, maybe think of putting in reamp circuits, stuff like that. Further software development, the Cosmo microcontroller and Python library needs still some work. A good framework for the instrument library, and we're already looking into how to deal with possible multi-core parallel processing. So, yeah, and of course, as you can see from the boxes, it's a quite tight fit. So there's things to go for the mechanical, and of course. One other exciting prospect is the other applications that's possible with this Cosmo technology. So put it into stack several Cosmo hats together, put this into to build installations or whatever, or self-contained instruments. There's a lot of possibilities there. This is just the start of to get a good framework and technology going. So thank you. If you have any questions now, or you can contact us on Gmail or Facebook. Yeah.
Thank you. Thank you, Alex. Thank you, Bernd. Any questions? Yes, Rory.
I just have a few questions. I'll just ask you all the questions first, and you can answer them one by one. It's easier. First question is it possible, or are you going to implement a way to swap between patches from the board itself? Second question is, in terms of the channels, are the channels fixed channel names? Or and are they defined in the include the .inc file? Because in the example that you showed, there was no mention of chan get. It was hard to see from the CSound code what was actually, which channels were affecting something. So they're just two questions I have. Thanks.
Yeah. Just to take the last one first, yeah, the channel names are set at the moment, but of course it's no problem changing that. We just want some things that it's easy. So if we go into, you can see the include files here, edit. So it's just basically like that. So it's sending out P0, P1, etc. for all the analog stuff, and for the GPIO, we're sending actually both. We're doing the code to do either momentary or toggle switching in the Python code, so it's just sending double channels. But if you want to change any of this, you can just go into the Python code and change it here. So it's just, yeah. And the other was, what was the other question? Well, there might be, we don't have a specific plan for that. That's sort of part of the how we will deal with the instrument library, I think, in terms of shutting on and off instruments or instances of CSound or something like that. But I mean, you could also expand this into having some sort of display or something to change between, so shut down one patch and start up another. But we don't have any specific technology plan for that at the moment. But that's probably a natural extension. Yeah.
Thank you. Any questions? Okay, I guess that's it. So, thank you, and I guess it's time for... Yes? It's time to make some music, right? No? So you just lay your saxophone on the table, like... Okay. Thank you. So, I give word to Oyvind Brandtzæg.
For the moment, we just have to do the workshop. It might be possible to sell them.
Are you okay with mic? Works? Yeah.
Okay, this talk is about an art project called Self. It's an artificial intelligence that I made together with a colleague at NTNU, Axel Tiedemann. The reason for exploring artificial intelligence is that it permeates more and more areas of daily life. We have all these apps and helpful gadgets on our phones to find our way and such. And experts like Ray Kurzweil says that self-aware artificial intelligence is within reach in our lifetime. So it makes sense to start exploring this in an art context. I brought a version of this installation here, displayed in the foyer, in the breaks. And to give you a context of the original installation, I'll show a video of like the hardware and how it was built and such. We wanted to build a moving head robot, so this is during summertime in my garage while the kids were at the beach. I got a lightning head for stage lighting, moving head, stripped out all unnecessary components. We have an Arduino with a DMX shield controlling the motors and a very preliminary version of the controlling software here. And well, it moves. So yes, sunny middle of Norway. Okay, a little bit later, I mounted microphones on it and used spatial panning analysis to allow the robot to turn towards someone speaking to it. So this is what I'm exploring here. I'm making these noises and making the robot turn around. The face painted on it is just to remember which is front and which is back of the robot. So this is an example of C-sound inside, I guess, applied C-sound. This is how it ended up looking. And you can see there's no attempt at making it look like a human at all. There's a very raw expression with all the components visible. It has microphones for sound input, camera on top, and a speaker on top, and a video projector. So, a little bit more about the software system. We have all the audio is handled in C-sound, automatic audio analysis and segmentation and recording. There's some audio analysis also in an external library that I will tell you a little bit more about. And the rest is Python. So when we have an open microphone in a public room like this, we have to automatically calibrate the audio levels, do noise reduction, and also suppress the sounds that the installation is making so it's not recording its own output. So at startup, we measure the input audio level and make a noise gate curve as a table. And this table is used later as a lookup table for the noise gate. We also do a spectral analysis to create a noise print, which is subtracted from the audio inputs during the during runtime. And the sounds that the installation is making is delayed according to the total system latency that we also measure during calibration. And the spectral analysis of the output is then subtracted from the input from the microphones. So it's quite a clean recording that we get from people speaking to these robots. Audio segmentation is done by transient analysis, and the transient analyzer is using a follow-to opcode to create an envelope, and that means we can have some control over filtering of the signal to get quite clean transient detection. There's also double triggering limiting, and we can also adjust like the sensitivity to repeated transient by adjusting the decay time. On top of this, we have an audio status indicator, which goes on when we have a transient, and it stays on for as long as there is sound coming in. And at the end of a sentence, we don't know if there is any more sound coming. So we keep the audio status on for a certain amount of time. And then when we're certain that the person has stopped speaking, we stop the recording. The reason I'm telling you this is that this creates some extra silence and some extra material. And training an artificial intelligence is quite computationally expensive, so we want to reduce the amount of material that it has to process, meaning that there are also some filtering mechanisms for very coarsely extracting interesting parts of the audio that we record. So essentially, we skip all signals below a certain threshold, and we record to a temporary table. When the audio status goes off, we read through this table, and for each transient segment, we measure the maximum amplitude. And if there's generally a low amplitude, let's say there's the clicking of a heel or the closing of a door and nothing else really happening in this segment, we skip it. So before we write it to file. And all skipped segments are flagged, as is the segments going to file. So we can essentially reconstruct the original signal with pauses by looking at time markers. As you can see, the figure is cut off here, and there's more to this that is in the paper that will be in the proceedings. The rest is more about the audio analysis and how that is marked and segmented. But it's a similar system to this for that as well. So then we have been here, audio analysis and segmentation and recording, and we're now going to the audio analysis called CARFAC. CARFAC is a cascade of asymmetric resonators with fast-acting compression. This is something made by Richard Leon at Google, and it runs as a C++ library that we just call on the sound files produced. This may look vaguely like a spectrogram to you, but it is more like a model of the inner ear. So the nerve cells in the inner ear each have their specific frequency that they respond to. And the frequency distribution in such a plot is according to the distribution of frequencies in the ear. And there's compression algorithm for each band, which nicely represents the way our ears compresses incoming sounds. And it also allows to model frequency masking effects that we normally have. So some frequencies might occlude other frequencies. These images are actually used to compare similar sounds to each other. So similar images are similar sounds. This is a representation of the well-known hello world. And you can see two quite similar instances. This is intelligence. So when the self entity wants to make a response, it will try to assemble a sentence of words that it has learned from people interacting with it. And there's an association system that takes one word that you have said as a seed and then create a sentence around this. And each word that it has learned is classified in different categories. Words heard in the same sentence, heard by the same face, its position in a sentence, and similar words, time, contexts, and so on. And this is a weighted system of associations, a little bit like fuzzy logic, to take all of these associations and collect them into one single score, which let us choose a word. And it uses the same technique repeatedly to assemble a sentence of chosen words. This is how it looked in the gallery. And one reason for having this is that the robot itself, with its speaker, plays the primary association. So this is what the entity says to you. It also has some secondary associations, and I think of this as the things you think about while you're talking, but you're not saying these things. So these secondary thoughts we wanted to spread around in the gallery room. So we used an ultrasonic speaker on a second moving head. An ultrasonic speaker can project sound to the walls and ceiling in a very lively way. And in addition to this, we take all inputs coming into the microphone and create some ambient granular textures of recent sounds to accompany this. The primary associations are played back with a slight modification. I tried to make a voice type that has a character of its own. So this robot has its own voice, but it's also possible to recognize who has said each word. So there's some frequency shifting of different bands and slight modifications. The secondary associations, I wanted to create a very slowed down kind of sonic character. So I use granular synthesis to, if we have a linear time with a dotted line there, we slow down time, and then we have an overlapping layer of slowed down time, so it progresses like this. So the idea was to slow down the audio, but still play it back at the same rate. In the hall here, you can hear this represented by the speaker playing backwards towards the window. You can hear some sounds there. Okay, the intelligence here also produces images. So when someone is speaking to it, it records the visuals that it sees. And it's not recorded as video, but it's recorded as, it's trained into a neural network. So when you have an audio signal and a visual representation, we train a neural network to produce this image when fed with the audio. And if you feed it with the same sound, the same image will come out quite clearly. And if you feed it with a sound that is quite similar but not the same, the image will be distorted a little bit. And if it's a quite unsimilar sound, it will be quite noisy. I figured this is the way a representation of how we remember things. When we don't remember it quite clearly, the internal image is also a little bit blurry. Here's another example of the video output. I'll show you a short video clip of how the robot behaved in the gallery just after a few days of interaction with the audience. It was displayed for a month in Trondheim and then 2 weeks in another gallery. Oh, we don't have sound. I should have sound now. Is it here? Here? Oh. Yeah, thanks. It's responding.
Si noe artig, da.
I have no idea where that association came from. So, to sum up this presentation, I'll show you another video giving a little bit more of a varied impression of what this can be.
Self er et kunstprosjekt hvor vi utforsker kunstig intelligens og hvordan den kan sammenlignes eller stå i forhold til en menneskelig intelligens. Den roboten vi har bygd er veldig enkelt uttrykk, og det har vi gjort litt med vilje. Den har mikrofoner for å ta opp lyd, kamera for å se dem som snakker med den, og den har en høyttaler for å spille av lyd, og en projektor for å spille av bilde. Når vi starter denne roboten, så kan den ingenting. Det vi ønsker å se på er hvordan den lærer, kun fra sensorisk input. Og når noen snakker med den, så lærer den seg de ordene den hører, eller de lydene den hører, og den kjenner igjen ansiktene.
Hvem er du? Hei! Når vi har laget Self, så har vi brukt mange prinsipper fra naturen. Måten den hører på er inspirert av det indre øret. Og de projeksjonene vi ser er ikke en avspilling, men det er en assosiasjon mellom lyd og bilde. Denne assosiasjonen ser av og til helt ut som en skrekkfilm, ut som en tåke, eller som et relativt klart bilde. Og det er en konsekvens av hvor mye lyden ligner på det bildet han har sett før. Self er laget sånn at om natta så tar den og drømmer. Da går den gjennom de tingene den har lært om dagen, beholder ting som er viktig og kaster bort ting som er uviktig. Forskjellen fra et menneske er at den er en maskin, og vi har enda ikke forstått helt hvordan hjernen er i stand til å lære på den måten den gjør. Derfor vil den ikke bli like intelligent som et menneske. Enda. Jeg kan si det en gang til og droppe den siste.
Okay, this Joiker professor, he happened to be there the day that we shot the video, so he was not part of the project, but it was a good candidate for testing that the intelligence could learn a very foreign language from what we had trained it on. All of the source code is available here. So hopefully someone else will also try to build this and modify it and refine it. Thank you.
Thank you, Owen. Thank you so much. Please, your questions. Anybody has a question? Oh, Ian? Yeah, just shout very loud.
When I see something like this, there's kind of a mixture of there's sort of fun and amusement because the thing looks funny, but there's also a sort of a sense of fear and terror, I think, which is kind of programmed into us to respond to something like this. So I just wanted to ask what you find interesting about the public's assessment of this interaction with artificial intelligence or something approaching on artificial intelligence. Were people on the whole amused by it, or anybody find it disturbing?
Yeah, I think both ways, and actually some of the point of creating an artwork like this is to create like discussions about. Some people would fear that when we get a self-aware artificial intelligence, it will be like the RoboCop or sci-fi movies, and will take over the world, run around the streets with machine guns and stuff. And it's quite valuable to sort of try to create a discussion about this, and perhaps it's intelligence in a machine is not as humanly intelligent, and maybe it doesn't yet have the desires that we have and such. And one interesting aspect of working with this, I find, is that the more mental processes we are able to simulate in a machine, the easier it is to see what remains, what the machine cannot do, and what is then must be uniquely human.
Thank you. Any question else? Oh, Tarmo?
Thank you, very interesting. One question about the technical side, about how well it could separate the words. So you used the transient detecting, and did you check the recordings? So how well did it really catch out separate words?
The performance varies a lot over the span of a month. I mean, if you have a loud class of school kids coming in, the signal level is quite different than a shy single participator talking to it. It performs well enough that it is able to make some sense of the communication, but there's definitely still room for improvement.
And how did you program building up sentences?
The building up of sentences? Well, it takes what it thinks is the most significant word of the last sentence it has heard, and use that as a seed, and then uses the association techniques that. So it tries to find similar words or words same by the same face, and words said in the same context, and then build up a sentence by that. And if no one is speaking for some time, and it sees a face, then it will search for a word that it has learned from this face, and to initiate a conversation.
What do your children think of it?
My children, they totally love it. We have also had a lot of school classes coming in to talk to it, and also to create a discussion about, I mean, intelligence machines and yeah. Thank you.
Thank you again. Thank you. Ladies and gentlemen, Kita Toshihiro in several minutes.
Start. Hello. I will show you some, how can I say, the kind of not so high level, but that kind of primitive, some example of the, how can I say, C sound usage. And let me, how can I say, do some demonstration in this time to make my presentation very short and quite practical information. So would you, if you have some smartphones or tablets, or would you please follow these instructions to take part in my demonstration? That's what I presented in the WebAudio conference in Paris this year, in January maybe. So first you find the Wi-Fi access point called this. It's kind of strange name. And and this time, please maximize your volume of your smartphones or tablets. And laptop is also, how can I say, acceptable to this system. And yeah. Okay, you can hear sound from your smartphones itself. And I will play just a part of the piece. The final part of the piece I presented at the WebAudio conference. And at least I have to make some explanation on my system. So one possible, very simple explanation is all the files are on that side, so see the files. That's all. And this, how can I say, a PDF file will be included in the proceedings set. That will be maybe handed to you tomorrow or tomorrow, maybe tomorrow. So in the proceeding, you can find the quite brief explanation. And Yeah. The information you send to the server will be processed also in the C sound process. So and I can control the don't be too excited. Touch the how can I say? Not very often, but the kind of how can I say? Just sometimes, maybe 1 second, one time, or something. Because I experienced the high load to my C sound process. That will be as you imagine, the chaotic, glitchy sound will be, how can I say, heard. So my C sound code will be triggered by the touching operation, kind of. As soon as you touch, the sound will be heard. But the sound will be controlled with my OSC app in my hand. And of course, in addition, the regularly looped sound will be added to the sound. That is basically not controlled by this app. And the sound from your smartphones are also controlled by some this kind of how can I say? Keep touching your smartphones. So I can control all of the volume. Yeah. Your volumes. Yeah. Now. Yeah. So if I set the volume lower, the sound will disappear. And I can control one of your smartphone like this. Maybe one person can play the sound this time, and another person over there, and maybe one more is added like this. Yeah. And now it's muted all, and I can how can I say, volume up all the participants. So try all of you to touch your smartphones now. And also the sound from C sound can be added. As a background music of your operation, I will explain quite briefly. Some mechanism of my system. C sound code is very simple, quite not so, how can I say, special. It uses OSC listen opcode as accepting OSC message at the 16 ports. And as I would like to accept all the smartphones or tablets without any dedicated apps, so I just how can I say, simple rectangle area like this, and but this kind of page will be easily pinched in, pinched out if you operate the screen. So I have to take how can I say, make some decoration like this, as I wrote in my proceedings. And converting HTTP data to OSC UDP data is done by the OSC PHP library that is released on the web, open to public. And I use the and OSC app for controlling the total sound. And I forgot to show you some another aspect of my system. That is the visualization. Yeah, please touch your smartphones now. All the operation data will be visualized on this, how can I say, page like this. So you can join the on the screen also. It's not clear the which is which. So, but the certainly you are the one of the points. And sound, of course, is how can I say, controlled by the also the same data. That is done by the JavaScript library called d3.js, and I use the WebSocket communication that is on PHP, not the JavaScript, not .js, but that's also WebSocket communication to display the visualize the data in real time. Yeah. as I said, all the files are on this website. So yeah, that's all. Thank you very much.
Thank you. Thank you. Any questions, please? Tarmo.
Thank you. Please, can you tell about this OSC PHP? So this is the bit of code that converts the usual GET messages to OSC. Is it written by you or it's existing?
So may I have a question? I have a question on scalability. Like, if our network is so great, because I'm interested actually in Internet of Things. So every kettle, every sink and thing, yes, everything is in the network. So could it be applied to this kind of system somehow? Maybe you could give us some, I don't know, hints or ideas. Like maybe we should cluster it.
Yeah, that's possible. But if the network is very weak and raw, the network speed is raw, the packet is kind of naturally filtered. So that means that the C sound, the road to the C sound process is reduced. So that depends how the network performance is affect the to the C sound sound generation. Yeah.
Any other questions, please? Okay. Thank you, Kita, for a wonderful presentation. Thank you. We have a very short break, and after we have Andres Cabrera from California, I guess, right? Hi, Andres. Do you hear
Hello,
us?
yes, I hear you.
Okay. So, we continue our conference, the last session for today. And welcome, Andres Cabrera. So, we continue our conference session for today. And welcome, Andres Cabrera.
Hey, thanks. Can you hear me?
So, we continue our conference.
There seems to be a long lag.
And welcome, Andres Cabrera.
Okay, thanks. Can you guys hear me? Can you hear me? I can hear you well. There seems to be a long lag. Okay, just did that. Yes, I'm speaking. Can you hear me? Okay, so I'm going to get started. Before I start, how much time do I have? Okay, excellent. So I'll keep it nice and sweet. Okay, so thanks everyone. I'm so sorry to again have to miss the C-Sound conference. I wish I was there. You must be having so much fun. So I'm going to talk today about oops, let me see. Okay, can you see my screen there? Okay, but it's just let me see, share screens. Okay, you should see it there. So I'm going to talk today about, give me a second, why? About interactive sonification with C-Sound, right? Sonification is this process of rendering information and interaction as sound. And there's three major kind of ways to go about it. Audification, parameter mapping, sonification, and model-based sonification. Audification is this direct mapping of any type of one-dimensional data to an audio signal. For example, and this is the typical example, earthquakes, right? So you can see here the output of a seismograph, and then you see an earthquake here, and then you can just take that one-dimensional set of data points and then just map it directly into sound. There's a parameter-based sonification where your data is actually used to control parameters of synthesis, right? And what the synthesis technique is up to the designer. It could be FM, or you could just directly control the frequency of a sine oscillator, or you could control parameters of granular synthesis, whatever, right? And one of the typical examples, classic examples here is grabbing something like stock exchange data and then mapping it to something like frequency, for example. And then you can see the trends in data, and you can also perhaps hear how two stocks might move together, or you can detect some correlation between the movement of different stocks. And finally, there's model-based sonification, where the data itself is the model. In other words, you don't hear the data until the user interacts by exciting the model somehow, right? There's no kind of fixed way to do this, and there have been many approaches, and it's very kind of ad hoc. For example, you can use physical interfaces for data scrubbing. So if you imagine your data as, or kind of model your data as something happening in 3D space, then you can use some 3D physical interface to hear the data as you move. So you get you start interacting with the data as if it was a 3D virtual presence. Or, for example, another technique is to interpret data as a multidimensional gravitational field, right? And then what the user does is shoot particles into this field and then listening to the velocity. In this case, what happens is that if there's clusters, these particles will tend to start gravitating and moving around the clusters, and that will generate a very different sound than if the data wasn't very clustered. So this will help you kind of understand the data, how it clusters through listening to these particles you're throwing in, right? And there have been many other proposed techniques related to, for example, modeling the way crystals form and so on, right? So this is very kind of ad hoc, and you can basically do anything to turn your data into a model. Then I like to make this clear separation between sonification and sonification design, where sonification is the result of sonification design. So you first have to design your sonification. You have to choose what technique you use, what if you do parameter based or parameter mapping sonification, what kind of synthesis technique you use, how do you map the parameters, how do you scale them, what data you use, etc. Right? So the success of a sonification depends on how well it was designed. I think, and from my experience, I feel that sonification design is an iterative process of exploration, right? It's a bit like composition, where you maybe try things and then go back and revise. So, but sonification is this mix between aesthetics and being able to extract things from data. So this is often the goal. So you try things out in different mappings and then try to see what works, right? So it's often the sonification design process can be a tedious task, because I feel the tools out there are often not very comfortable, and they produce more friction in this process. The sonification workflow is often load your data or acquire your data somehow from a web API or from some data file, data format, CSV, whatever format. Then you go through the sonification design process, where you try out stuff, you choose how you're going to sonify the data and what part of the data you're going to sonify. And then finally, once you finish the design, you interact with the sonification. In other words, you often leave some controls open or some other way of interacting with the sonification in order to explore the data or to show different aspects of it. So here's where I think that it's good to combine two different languages for this, right? Python is really good at loading data and interpreting data and slicing data into pieces and handling massive multi-dimensional data arrays and data formats. And C Sound is really good at producing sound and doing interactive sound. Right? So I think using both Python and C Sound and connecting them as part of the sonification workflow actually results in a really comfortable setup. That's why I wrote C Sound. That's a Python module that's assigned to be used in the IPython notebook. I'll do a really quick demonstration in a second. Hopefully it bridges the gap between the data and sonification by combining Python and C Sound. And hopefully it leads to better sonification design workflow. It builds upon previous work by François Pinot and Jacob Joachim, who have written some Python wrappers for C Sound and some Python communication for between C Sound and Python. Right? But IC Sound is specifically written for the IPython notebook to leverage some of those options. So let me go into the demo. So this is the IPython notebook. If you haven't tried it, I highly recommend it. It behaves a lot like, say, a MATLAB or Mathematica system, where you basically have these cells where you can type Python code and execute it interactively. So the first thing you do is you import the IC Sound module, and then you create an IC Sound object, right? Then you start the engine. Right, and it tells you C Sound server started. You can see that the start engine has some parameters, sampling rate, control samples, number of channels. So some of the stuff you would put either in the command line flags or the C Sound header, right? It runs in a separate thread, so it doesn't block Python execution, right? If I try to start it again, it tells me, okay, it's already running. So this IC Sound engine is already running in the background. Here's where I leverage the IPython notebook option. So I can actually use these symbols that indicate that this is a magic command. So these are IPython magic commands. So what this indicates is that this whole cell is going to be C-sound code rather than Python code. So I can do that, and this is actually sent to the C-sound running instance. Then what I can do is I can do this, right? So this is, again, C-sound code, but then where did it print, right? The log, because C-sound can be very verbose, is kept kind of internally. So here's where we can do it, and you can see there, this is the printout from those commands. You can also use the clearlog function if this is getting a bit unwieldy. You can create ftables directly from Python lists or NumPy arrays. And then you can use these plotting facilities that make them look more C-sounding, right? So the kind of graphics that we've grown used to. You can also get values from, well, either the whole table data or just individual values. And you can also use the gen functions, right? So you can see here I've used the C-sound gen functions. I can also get slices of the data and so on, right? What I did, and this is what took a lot of the work here, is that I use C-types in order to be able to do very fast copying, well, or as fast as possible copying from Python to C-sound. So here I'm copying these tables that have been generated randomly from Python to C-sound. This would be significantly slower if we were just copying Python numbers, right? But because we're passing internally C arrays, this is much more efficient, right? And then I can just get the table back from C-sound. So this table that I'm showing here, I'm getting it back from C-sound. You can also send instruments. If there are syntax errors, what's good is that it actually shows me the C-sound syntax error here, right? In this case, the parser failed. Then when I make a write instrument, there's no error message, right? I can set and get channel values, right? So this is all happening in the C-sound engine that's running in the parallel thread. I can also record the output, right? So I can press this and then stop record. And if I had my right, I don't want to turn on the sound too much, otherwise we'll start getting this crazy feedback. So this is again something else that took a bit of work, and I had to modify the perf thread, the C-sound perf thread function to be able to have this recording facilities there. So you can just start recording, and whatever C-sound is playing at the time will be stored in this audio file. You can also actually create remote engines, and then you connect through UDP and send commands through UDP. So you can have an IPython notebook on one computer and your C-sound engine running in another one. Right? You can stop the engine, etc. And I'm going to quickly show some examples of audification. So this is a line that's reading from a web API some earthquake data, right? Then I massage it in Python, and this would be something that would be very tricky to do in C-sound, right? So I'm just kind of breaking up the data and storing the values there. I'll just keep going while this computes. Then I'll start the engine, and I'll fill the table with the values that I got from the web API. Then I'll make an instrument to play things back, and you can see that I'm going to be using table 1, right? So this in this case is P4, right? So I'm going to be playing the table directly through an oscillator, right? At whatever amplitude makes sense, and the duration and the speed will depend on the note that triggers this instrument, right? So I'll just send this code, and I'm going to turn on the microphone for a second. I'm going to be playing the table directly through an oscillator, right? At whatever amplitude makes sense, and the duration and the speed will depend on the note that triggers this instrument, right? Well, so hopefully you heard some kind of noises in the background behind my voice, and you can actually hear the earthquake and the earthquake replies. And the fact that it sounds orally similar can tell you that this is, in fact, a reply from the earthquake, and you can hear the repetitions. Different earthquakes produce different sounds. Some of them sound scrapey, some of them sound very distant or reverby. So this has actually been used to characterize earthquakes. Another quick example, I can get financial data through a web API from in this case, from Yahoo Finance, and I can select the symbols and so on, and then I massage the XML to just get what I need, and then I just fill the tables, right? So here they are. This is Google data, and this is Microsoft data. And then what I did here was I created an FM synthesizer. Well, actually, this is phase modulation, and I connected one of the stalks to the carrier frequency, and the other one, so table 2, to the modulation depth and the CM ratio, right? And then I can just play this phase modulation, and I connected one of the, right, so you can hear the crazy sounds there. And then you can actually, for example, get a channel, right? So if I play this now, and then I can just play this. Right, so you can hear the crazy sounds there. And then you can actually, for example, okay, so hopefully you could hear some of it, and as I changed this factor, you could hear it becoming more wobbly or less wobbly, or with the high values, it became kind of brighter, and so it changed the sound. So I can change these parameters dynamically from Python in any way that I need, right? So if we could hear it kind of more clearly, we could clearly see, well, we would hear the sort of the center frequency moving along the lines of one of the stalks, and then the brightness or the wobbliness would be determined by the other one. So you could actually hear them together in a way that makes some interesting sense and gives you some other insight on the data. Okay, so I guess that's basically it. I'll keep it short, and maybe I'll open it up for some questions if there are any. Actually,
please. Any questions for Andres? Andres, thank you so much. Any questions to Andres? Rory, would you like to type something? Oh. Andres, you hear us?
Yes, hello, I'm here. I figured out the problem. I had the YouTube video running in the background, so that was the...
Oh, infinitive loop. Okay. Thank you. Thank you for presentation. And if anybody has a question, is welcome. Okay, Andres, thank you again. And our next speaker is Joachim Heinz. Welcome. 2 minutes. Yeah, 2 minutes. Execute. Because I was thinking just
Yes, just by.
this one.
Which one?
This one.
Oh,
There's
all right. And now the slides.
And you got this microphone?
Yes, wait a minute.
Actually, Joachim brought this book, this heavy book, multiplied by how many articles of this book you multiplied by
What? 7.
by 7.
He,
So.
not me, Alex, Arsalan, and Ian brought.
Oh, so we could divide it by 4. Okay. Kind of mathematical joke.
We are sharing, of course, so mathematics is not the final solution. Yeah, so I would like to introduce you to Knut and Alma. These are two partners for live electronics with spoken words. So actually the idea is you have this a small speaker like this one. You get anywhere, you have your sort of readings as a poet or whatever, or as a performer, and there is something which comes out of this little thing which may help or hinder you. The aspects of both are quite different. Knut focuses on the rhythm of the language. So when I speak now, it is something like this, what we recognize as internal rhythm of the language, which is of course irregular. And Alma has a completely different approach. She focuses on isolating sounding units of the language. So I start with Knut, and oh, I see that this, oh no, here it's okay. It's just on my screen too small. So I start with Knut and try to show you what is the goal and how tried I to achieve this. So this is the famous, the quick brown fox jumps over the lazy dog from the C-Sound manual. So we see clearly the accentuations, the quick brown fox jumps over the lazy dog. And what we would like to achieve is that we have a detection like this. I tried several things like onset detection, and then I was most happy with using the PVS pitch opcode in C-Sound, which actually looks for the spectral peaks. So the accentuation is very much connected to the detection of vowels, and vowels are the harmonic part of our language. So when we look for something which has strongly pitched, is strongly pitched, so has a peak in the pitch area. We expect it from pitched sounds, but not from noisy sounds. And this works actually quite well. So I show you now the basic code in C-Sound. The purpose is something like this. You hear from this speaker the detection, and from that speaker the original sound. And when I use the PVS pitch opcode, actually I feed in the frequency signal and a threshold which says only something which is upon the threshold will be recognized. And now I look to the transitions from below the threshold to upon the threshold, and that's it actually. So what I do here, I get the live input, I set the threshold I do the FFT, perform the FFT, and I use PVS pitch in the way I described. And then for this, if the previous is below the threshold and this one is above the threshold, then I trigger any event. And the result is this. So you see we are not yet there. We are here. But actually the result is not that bad. All we have to do is to remove the repetitions. So the next step of code is that I introduce a simple look for a minimal time, after which only a new result is considered. And then the result is like this. Or in images like this. So this is good enough for me to work with it, because it's not a scientific approach, it's something which I want to use to play with it. And now I show you the basic setup for Knut. It's, of course, this is only one possibility. I mean, this is a quality, and it's on the same hand, it's a difficulty that we have so many possibilities. All Knut does on this step is to analyze. And what I do with the result of the analyze is, of course, up to us. So I can trigger any instrument which does something. What I show you here is some collection, and it can be very different. And after this, I will perform a little other possibility. So here, now I switch to the other microphone. This is easy. And now I show you one application, a little poem from Kurt Schwitters. This is the number poem 12, or in German 12, from Kurt Schwitters, my Hanover companion. And I have prepared a little performance which uses some presets. And you will see I just do it here with the mouse and sort of accompany this poem. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Thanks very much. This was Knut and now Alma. As I already said, Alma is very different. She looks for sounding units. So what I do is actually I record all the time what comes into the microphone, and I look whether the RMS value is below a certain threshold for a certain time. And if it's the case, then it will be considered either as the beginning or as the end of a sounding unit. This is very simple. It depends only on the threshold, of course, and on the amount of these sort of pause. Actually, in my thinking, it's a pause, it's a break. So I show you how it works. What I show you here now is the threshold is here, it's minus 30 dB, and the minimum time you see here, it's currently 0.01 seconds. And I can play back the first 10 analyzed units. So it's just for demonstrating. Ich zeichne einen Kopf. Dieser Kopf ist nicht sichtbar. Ich zeichne einen Kopf. Dieser. Okay, now you hear that it somehow is related to a dimension of a syllable, but there are many surprises. And it depends, as I said, on both the threshold and on the minimal silence time. So when I do it, when I reduce the silence time, it will be something like this. Ich zeichne einen Kopf. Dieser Kopf . I think it's obvious it's now more or less phonemes. So I can adjust the size of the sounding units mainly by this parameter and also with the threshold. Okay, so just to show you some results, this would be the result for the Fox with a minimum silence time of 0.04 seconds and a threshold of minus 40 dB. This would be with a smaller minimal silence time, and this would be something which adjusts the threshold actually much better in this case. Because it's stable, but of course for live input you have more problems. So I would like to show you another example for Alma. It's a text of Ludwig Wittgenstein, and what I did is simply I introduced some pauses in the text, and I programmed Alma in a way that she actually behaves in a similar way. So she creates some new words, parts of sentences, and then she makes a break and she does it again. So we are sort of on the same in the same mode. And Oh, by the way, I forgot to show you the capability of playing MIDI, but if we have time, I can do it later. First, I do the Wittgenstein text. It reminds us that the history is always there, right? So. Ich zeichne einen Kopf, du einen Kopf. Ich, was soll das vorstellen? Ich, das soll einen, ich, eine Frage, was eine, ich, es, ich, sieht, sie zeichnet was ihm aber nicht ähnlich sei das sei du zeigt aber als ich sagte es aber es dem du es sagt, macht die N, aber einen Zusammenzeichen. N, du, Zeichen, sie macht von einem du, eine, welcher du Zusammenhang ich ein hatte denn bestanden? All right. Thank you very much. So actually I missed to show you the MIDI live possibility to play Alma, but Gleb told me that perhaps we will have a performance here with a Russian performer with Alma, so I think it's better to get it then. So thank you very much for your attention. If you want to have a look, there are some recordings in particular about Alma from the French performer Laureline König on my website. This morning I saw that I forgot to put something about Knut. I will do this in some days. Yeah, if you have questions, please. Yeah, it was both. Actually, I would love to work with several people. I worked with Laureline, and I'm also working with my performance theater in Bremen, and I do it on my own, as you saw. So this is nice for me to get several feedbacks and to adjust the instrument for several situations and persons. We are now with Laureline working on a touchable large interface so that you do not have this small MIDI keyboard, which is of course not good for real performance. Something like this is also on the list, yes.
Any more questions, please? Alex?
Yeah, you decided to just play back the samples in the original speed, not backwards or anything, so do you want to keep the character of the natural voice? Yeah, thanks for the question, because I forgot to explain the modes of Alma. This is only one mode. This mode indeed keeps the samples in the way you described. I have 3 other modes. One took very small snippets and replace it like a wave. I mean, like from a seashore. It sounds a little bit like granular, although it's not granular. The other one is like this additive thing which you analyze this snippet. And you take, for instance, 5 most prominent partials, and you also mimic the movement of the partials in this language. So there are many possibilities. I decided to work out 4, but these are sort of studies about one of them, because I thought it's only very important how the performer reacts. It's not only about the feedback of Alma, but it's also what do you do then as a performer with it. And I wanted to reduce it.
Okay, thank you. Very nice presentation. Thank you. Now we have a special part of today's session. We have Tarmo Johannes, yes, with his remote performance. Probably Tarmo could tell us a short introduction for this performance. But unfortunately for our global viewers, we have to cut the line because of some internet issues. So, but you could join us in this game, yes? You could join us. So, see you tomorrow, I guess, everybody. And cut. And now we have Tarmo.
I probably need a couple of minutes to get finished.
Yes, a couple of minutes for Tarmo to make connections. Tomorrow we will continue our sessions. We have several other papers tomorrow. Tomorrow we start at 10 again. And tomorrow we have a stereo concert for fixed media at 6 p.m.